Hi everyone, I'm Junho. I'll be sharing our work, Preference Consistency Matters for short, in collaboration with Juyeon, Juri, Usok, and Youngdae from Samsung SDS. I'll begin with the motivation and wrap up with the conclusion, while Juyeon and Juri cover the main content. Preference learning datasets often suffer from annotation inconsistencies, which distort preference patterns and reduce model reliability. These inconsistencies stem from annotators' diverse backgrounds, conflicting criteria, and the complexity of human preferences. These are also seen in LLM-based annotations. Since manual curation is costly and impractical, scalable automation is needed. In this work, we propose a simple yet effective preference data curation method based on self-trained proxy models that learn consistent preference patterns and detect inconsistencies between the patterns and the annotations.
Hi, I'm Jian. I introduce related works and our self-creation method. Existing methods don't address preference noise in preference labeling. Assume a fixed error rate for flipped preference labels without a systematic identification of these errors, and also overlook the quality issues in preference dataset. But our self-creation method is a novel subset selection method aimed at improving the consistency of preference annotations, thereby addressing the limitations of existing methods. Our key idea is the use of proxy model trained on the preference data itself to identify inconsistencies in preference labeling. Since the proxy model trained thus can effectively learn the dataset's consistent preference patterns. This enables naturally to identify preference inconsistencies. In most preference datasets, we found lots of preference inconsistencies as visualized in the figure below. Let me elaborate on the figure on the next slide. We analyzed the ultra-feedback dataset as a case study to show the impact of consistent preference data on DPO training. 5 subsets, D1, D5, were utilized to compare performances of DPO, with D1 using the whole data as a baseline. Our proxy model identified inconsistent preference data which was used in D2. D5 using only consistent data performed best, while D2 using only inconsistent data did worst. D5 used only consistent data yet it outperformed D1. This shows the impact of consistent annotations in preference learning. On the other hand, in D3, the chosen reject labels of D2 identified as inconsistent data were flipped, but the DPO performance was not significantly better than that of D2. This indicates that D2 is not considered as mislabeled. Preference inconsistency occurs in the context of noise labels, including ambivalent data with divided preferences and ambiguous data with high preference uncertainty. When trying multiple annotations using GPT-4, 7 out of 10 times were inconsistent in the sample from Figure 1, and 2 out of 4 times were inconsistent in the sample from Figure 2. These better not to learn data often hinder meaningful preference learning. To deal with preference consistency issues in datasets, we propose a self-creation method for preference datasets. Here's how it works in 3 steps. First, training a proxy model on the preference datasets. Next, re-evaluating the quality of responses within the dataset to identify inconsistencies between model predictions and given annotations. Finally, selecting a consistent subset of preference data by screening out inconsistencies. In the way, our self-creation method identifies inconsistent preferences without relying on heuristics. We evaluated our proposed self-creation method from three perspectives. First, a range of popular preference data sets. Second, various preference learning algorithms. And third, different base models on the proxy training process.
Hello, I'm Jury, and I'll start by introducing the first of our three main experiments. We evaluated self-curation using the Llama 270 model on various preference datasets, both human and LLM annotated. For each dataset, we compared a baseline model trained on the full data with a self-curated model trained on a curated subset. The self-curated model consistently outperformed the baseline across all conditions, demonstrating the effectiveness and generalizability of our method. To further validate the effectiveness of our approach, we extended our experiment to two additional preference learning methods, CDPO and RDPO. Across all three methods, our self-curation approach consistently and significantly improved performance in every setting, highlighting its adaptability to various preference learning algorithms. Next, we examined how the capability of the proxy model influences the effectiveness of self-curation. Our findings show that self-curation is largely independent of the specific proxy model used, as long as the proxy has enough capacity to learn consistent preference patterns from the dataset. To validate this, we trained proxy models using different base language models, including Pi3, Llama 2, and Mistral, under identical training conditions on both the ultra-feedback and entropy helpful datasets. Across all cases, applying self-curation led to better performance, regardless of the choice of base model. To demonstrate the qualitative impact of our method, we present generated responses from models with and without self-curation. These examples show that self-curation enhances safety, appropriateness, and alignment with human preferences. In the Beavertails dataset, the self-curated model produces noticeably safer and more appropriate responses. Similarly, in the Entropy HH dataset, it generates more helpful and human-aligned outputs. In this section, we present additional analysis to further explore the potential of self-curation. Figure 1 shows that self-curation achieves strong performance even with less data, quickly surpassing the no curation baseline as dataset size increases. We also examined whether removing samples with small positive reward differences could further improve results. In Figure 2 for the ultra-feedback dataset, removing around 15% of such data led to peak performance, suggesting that better threshold tuning may yield further gains. Since self-curation is performed before training, it introduces some initial overhead. However, it enables faster performance gains with less data and can be further optimized with better thresholding. Lastly, based on paired t-test and response length analysis, we found no significant difference in length distribution between self-curation and no curation settings. This indicates that the performance gains are not due to longer responses, but rather to more detailed and human-aligned generation.
In summary, we demonstrated how inconsistent preference data negatively impacts preference learning. Our proposed self-curation method provides robust and heuristic-free alignment across various algorithms and proxy models. This work lays essential groundwork toward advanced methodologies in preference learning. This ends our presentation. Thanks for watching.